So today, my topic is OCT technique for neuroscience and ophthalmology. So I've been working in OCT for almost more than 10 years, something like that. So my research in CLC is mostly in construction of two-photon microscope and OCT as well. So today I'm just going to use this opportunity to introduce to you some of the techniques being used for neuroscience and ophthalmology. Most of them come from my previous research. Yeah. So this is the outline. So I'll just give a very brief introduction about OCT for those of you that may not know what OCT stands for. And then I will give three specific, I would say, small topic. First one, to improve the penetration depth and spatial resolution using shortwave infra wavelength OCT. And then next, I will talk about using the visible light OCM to look at the mouse cortex. And then lastly, I will talk about using the visible light OCT to look at the retina. So first, I just want to distinguish the OCT and OCM by saying that they are essentially the similar technique. It's just that when you use high NA objective, it will become, people will call it like OCM, whereas for normal NA objective, we'll call it like OCT. So I'll come to this briefly. So OCT is based on light interference-based technique. It can produce cross-sectional image of tubic media such as biological tissue. So this I'm circling around is the first version of the OCT, which is the time domain OCT. So basically, you have a light source, which is temporarily low coherent. So for some of you that may not know what it means, it also means that it has broad bandwidth. And then in that case, it will give you low temporal coherence. So the light will usually go through some kind of like beam splitter to split, and one part of the light will go to the sample, and then another part of the light will be used as reference. And when they recombine and at the detector, when they travel the same amount of distance, they usually they will give you this kind of interference pattern, which I shown here. In which case, it is a very powerful method that can allow you to measure the distance of your object. So typically for OCT, usually the coherent gating is used to determine the axial resolution. So in this case, as I circling here, the coherent length, which is the coherent gating, which is provided by the broad bandwidth light source, meaning that when your bandwidth is broader, your this width of this interference will become narrower. So mean that it will give you high accuracy when measuring the distance in this case. So whereas the NA is still determine the transverse resolution. So this is the most I would say most unique feature of the OCT comparing to other kind of optical technique, because the axial resolution and the transverse resolution is more like decoupled, so they are not like directly related to each other. And then these are some of the formula I just highlighted here. I believe most of you are quite familiar with this. So basically, the transverse resolution usually is governed by the NA and the wavelength. But in this case, the axial resolution is governed by the wavelength as well, but it's also more depending on the bandwidth, which I mentioned earlier. So there's also another term we call it depth of focus. So most of you that came from other optical microscopy like confocal should also quite familiar with this term, which also determine the axial resolution for most of the microscopy technique like confocal or like even in some extent two-photon microscopy. So there are two main forms of so-called forward domain OCT. I probably didn't explain this, but basically, the forward domain OCT is quite different to the time domain in the sense that you still use broad bandwidth, but you use a spectrometer to capture the interference signal. So rather than in this case for the time domain, you actually move the sample because you want to find the location where you get the interference signal. But for the forward domain, there's no moving part in which the information is all captured using a spectrometer, and then you use a Fourier transform to get the same information as you get from the time domain. So as you may expect, the forward domain OCT is usually very fast, much faster than the time domain OCT. And because of that, usually you can increase the imaging speed, but more importantly, you get quite a significant increase in the sensitivity. So which is usually people will call like you get about 20 dB increased sensitivity. So these two type of forward domain OCT that I mentioned just now is there are two main forms. First is basically you send a broad bandwidth, and then you collect it using a spectrometer. So meaning that you collect all the light in one shot. Another way is that you can actually use a single detector, but then you sweep the color. So basically you sweep the wavelength across a broad bandwidth, and then you collect the each wavelength at one time, for example. So the effect is actually quite similar. It's just that whether you provide a broad bandwidth or you sweep at one shot, or you sweep the wavelength and to get it in a sequentially. So it's still the same that you get the interference signal, and then you can do the Fourier transform as mentioned here. So typically the signal is actually the depth information is encoded in the frequency. So when the depth is shallower, the fringe will be having lower frequency. But then when you have larger depth, where the light travel longer distance, the fringe will be higher frequency. So when you do the Fourier transform, you can actually separate three of these components as from three different depths. So this is how you get the depth information from the Fourier domain OCT. Whereas for the time domain, as I explained just now, you have to sweep across different depth, and then when you sweep around here, you get some signal, and then when you sweep around here, you get some signal. So it's actually much slower because you need a way to sweep the sample in this case. You want to sweep you want to sweep the depth in this case. Yep. So just one last slide for about OCT. So usually the scanning mechanism of the Fourier domain OCT is very similar to what you encounter frequently, like the confocal or the two-photon microscopy. So basically, you scan across the XY plane, and then because your information is already encoded in the frequency, so in other words, you don't actually need to scan the Z. So basically, you just have to scan across, for example, in this case, YZ, and then you stack up your frame, and that's how you build up your whole 3D volumetric information. So whereas for another type of OCT, which we call full field OCM, typically this type of OCM we use very high NA. So basically, it gives you one shot of XY plane. So because you actually detect this using a 2D camera, and then but you have to actually move the sample so that you can actually acquire Z information. So I don't want to describe too much about this full field OCM, but I just want to let you know that there's also another kind of OCM or OCT which actually called full field, and then the scanning geometry is slightly different from what you would typically see in the Fourier domain OCT. So I'm going to quickly go into the first part of the talk, talking about using the 1.7 micron OCT to look at the mouse brain in vivo. So most of you are quite familiar with 2-photon and 3-photon microscopy, and they are very powerful to give you very high resolution image of the neurons and other other cellular structure. Like this case, you can actually resolve the vessels and things like that. So and it has a very high molecular specificity because you can actually pinpoint what kind of cells being labeled, and you can without no doubt that knowing the identity of these cells. Yeah. Another very powerful technology called photoacoustic microscopy. So it can give you this more like absorption based. So when the light actually being absorbed by the particle, they will create they will actually emit some kind of like acoustic information. So acoustic is like ultrasound, like sound wave, which you can actually detect using ultrasound transducer. So that's where you form the image. This is why I call photoacoustic microscopy. So it's quite powerful in the sense that it allows you to get a lot of contrast from the absorptive nature of the cells. For example, you can get like the saturation of the vessels and things like that. So, but we know that if you want to look deeply into the brain, usually the high scattering skull and the brain tissue will prevent you to focus very well into the sample. So this is just an illustration of what happens when you have scattering and when you don't have scattering, and when you have scattering, what will happen to the light. So when you try to focus the light into a sample without scattering, basically you can get pretty well and tight focus in the focal plane. But then when you get scattering, you can imagine that the light being scattered away. So some of the light will actually lose when they travel down to the focal plane. And this actually also means that there are less effective delivery of the light into the sample. And then it also actually create a lot of blurriness because your light is actually scattered to other region, and it might actually excite things that it should not excite. So in this case, so in the same way, when the light being collected from the emission of the sample, so in this case, if we refer like fluorescence, so the light actually when there's no scattering, the light can actually come in pretty in a well-defined manner, such that the light coming from other region will not get detected. But then when there's a scattering, so some of the light that come from surrounding might actually also propagate back to your detection. So you can actually say that these are actually background noise that will actually hamper how well we can actually image the structure deep inside the tissue. So because of this, right, the penetration there is still very limited to superficial cortex. In this case, I just want to put an example showing that this is the stained mouse brain slice. I believe this missile myelin stain. I think this myelin stain. So basically, the darker region means that there are a lot of myelin fibers. So so in this case, this is the cortex is about 2 or 3 millimeter, and then this is the hippocampus, which actually responsible for a lot of the memory function of our brain. So far, I think 2-photon can only reach like up to 1 millimeter or 1.5. Even 1.5 is probably quite challenging. So it's still quite difficult to actually look at the whole brain, and we know that there's a lot of diseases that actually affect the subcortical region, which we are so far unable to access now. Yeah. So so far there are quite a few attempts to use OCT for mouse brain imaging. So OCT has some advantage that because they have very high sensitivity structure imaging with micro resolution, but as opposed to the fluorescence, they are not very specific because they basically just scatter light and scatter it back to the detection. It doesn't actually allow you to tell very easily what kind of cells that you are actually looking at in that case. So, but OCT usually can get much larger field view and much higher acquisition rate. So without any label, you can also get angiogram like this. So basically, you can actually visualize the vessels in the mouse brain, and you can also measure the flow using the Doppler effect. So that actually allow you to look at the oxygenation if you can actually use some kind of contrast to actually know how well what is the concentration of the oxygen in these vessels. So just going to skip through this. So there are just two main model that being used for imaging mouse brain, the thin skull and open skull. So they are, as you can expect, the thin skull is kind of like preferred for some application because it doesn't break through the dura. And then whereas the open skull is that it gives you generally better clarity. And then, but because you remove the skull, so it may actually affect the physiological insight. So there's a lot of attempt how to improve the penetration depth. So this is one of the earlier attempt that use longer wavelength. So basically, with longer wavelength, you can actually reduce the scattering of the light when it propagates into the tissue. So this is one of the recent paper, actually not very recent, it's like 2013. So they actually used 1.7 micron to perform like 3-photon microscopy. And they claims that because the light is actually less scattered in this wavelength, so they can actually reach deeper than the 2-photon microscope when they look at the mouse brain. Yeah. So here I just want to highlight a few advantages of using 1.7 micron or 1700 nanometer. So basically, there's higher water absorption. The backscattering could be reduced. And then it's also quite difficult to find a detector in this regime because most of the silicon detector they cut off at about 1650 or something like that. So but really the biggest advantage is like if you use this long wavelength, usually the scattering will actually decrease by a lot. So because the scattering is so bad for like looking at deeply into the biological tissue, right? Because it deviates the beam path as you have seen in the previous example, and it distort the beam wavefront and things like that. It prevents the tight focusing and cause a lot of blurriness. So it kind of like reversibly degrade your resolution and your signal localization. Yeah. So that will actually prevent you to look deeper into the mouse brain. So so here this is one such system we built using 1700 nanometer wavelength light source. So basically we use NKT superconductor light source, and then we filter out the beam to only use the 1700 wavelength. And then this is actually very similar to a typical OCT system. So basically we split the light to 50-50. And then one part of the beam go to the sample, and then one part of the beam go to the reference arm. And then they will be reflected back, and then it collected using the spectrometer again. So this application require quite unique in-gas line scan camera. And this camera usually they are quite noisy, unfortunately. So they are not like the silicon camera. Yeah. So when we look at the mouse brain, we notice that which is not unexpected based on how the tissue actually react to the light in different wavelength. So as you can see in this curve, so generally your blood actually is very absorptive in 400 to 600 nanometer. And then after when you go beyond the like 800 or 900 nanometer, the water absorption is actually like increased by a lot. So there are some region where people like to use like 600 to 900 nanometer, which they usually call the biological window, which you can try to look deeper. So on the other hand, the scattering generally reduce across the wavelength. So as you can see that because of this characteristic of the tissue, how the absorption and the scattering affect the light penetration into the tissue, there are a few windows that people like to use. So these are highlighted here. So visible light is one window, and then we have this near infrared wavelength. 1300 is a very dominant wavelength being used for OCT. And then what we propose here is we propose to use 1700 nanometer. So as you can see that when we move to longer wavelength, the absorption will start to increase. But then because the scattering actually reduced by a lot, so we claim that it will allow us to image deeper in this, which we also demonstrated in when we image the sand mouse brain. Yeah. So for the visible light, it's quite expected that we cannot reach very deep because usually visible light is quite absorptive by the blood. Yeah. So we also measure the attenuation of the light, which is one way you can characterize how well the light actually penetrate into the tissue. So we confirm that for when we use the 1700 wavelength, the attenuation is actually the lowest, which means that the light can propagate longer before being scattered in the tissue. So this is one way you can actually characterize how well the light can penetrate into the tissue. Yeah. So of course, we also confirm that the younger brain will actually allow us to look deeper because they are simply just less developed, and as they grow older, you have higher myelination, which are highly scattered, and it will actually also cause the scattering that that you observe. So also it's good to highlight that most of the a lot of the paper that they publish, like trying to look deeper, so you may have to pay attention like what kind of brain they use, like are they using like adult brain or they're using like very young brain or something like that. So from what I heard, it's still quite challenging to image adult brain, even like using 3-photon microscopy, which is one of the most powerful multi-photon technology for deep penetration. Yeah. So with the 1700 nanometer system, we actually look at the mouse brain and then we correlate with histology. So this one is showing the OCT images, and this is just a pictorial showing like what's the structure of the mouse brain. So if you can see, this is the hippocampus. And then this is a Nistal staining, basically just stain the cell body, and then this the myelin staining, and we stain the fiber, the myelin fiber. So as you can see, they actually quite closely resemble to each other in the sense that you can identify the blood vessels in this case. So and also you can also see the cellular the fiber structure, which is highly scattering in this case. And then lastly, you can also see the highly brightness signal here, which also correspond to the myelin fiber. So you can see in the myelin stain is highly dark in color because they are highly dense in the myelin fiber. So last but not least, they also allow you to see some cellular layer in this case. So in this case, this is a pyramidal cell layer, which is quite obvious in the Nistal stain. As I mentioned, this is staining the cell body. As you can see, it can actually appear as a dark band in the OCT image because the cell body are highly absorptive. So this is why you see it dark in the OCT image. So we also demonstrate that with the OCT, you can actually get the angiogram of the deep part of the subcortical brain, and this is a figure showing the white matter angiography, which is close to the corpus callosum. So just a quick summary. So microscopy imaging beyond 2 mm is still quite challenging, and even though the water absorption is higher in 1700, the high resolution can be demonstrated through the thin skull into the hippocampus, and then mainly because the multiple scattering can be effectively reduced. So we also confirmed that through the co-registered Nistal and myelin staining that there's a cellular and morphological feature in the subcortical region can be observed using the OCT technique. Yeah. So we also shown that we can actually visualize the vasculature in the deep inside the mouse brain without any labeling. Yeah. This part I think I will just skip because this one is talking about using OCT at even longer wavelength, 2200 nanometer. So, but if you're interested, you can refer to this paper, but I will just skip through this for now. Yeah. Then I'll quickly jump into the second part of the talk, which is using the visible light OCM to look at the mouse cortex. So for those of you that actually have some background in the confocal microscopy, you should be quite able to appreciate this section. So most of the OCT system, they actually have a shared illumination and detection part. So typically a good design criteria is that you want to have the overfill factor of less than 1 to minimize the loss when you detect the light. So because if you use the higher overfilling, then your detection efficiency will usually drop because your signal will lose in the detection part. So in this particular study, we use asymmetric illumination and detection optics. So basically, we employ high NA for the excitation, but we use moderate or low NA for the detection in this case. So this is actually very typical to typical OCT schematic diagram. So basically the light is being filtered and then sent to a beam splitter. So I'm not going to talk this about too much. And then in the beam splitter, as I mentioned before, it's split to the sample arm and then the reference arm and the sample arm. And then where the light will come back and will be detected here. So in this particular example, so we actually use a larger focal length in the collimator so that the beam is become very large, so that when it comes to the objective, it's overfill the objective. So mean that we can actually appreciate the full resolution of the objective because we overfilling it. And then, but in the detection, we actually use a moderate NA so that the detection will be maximized to minimize loss. So this is not possible if you use geometry like this. For example, in this case, in this case, because your excitation and your emission is actually using the same objective, so you cannot actually control the NA independent. Yeah. So we actually measure for 3 different overfill factor, and then we actually compare the resolution that we can achieve. So you can see that the resolution can improve by from 1.3 to about 1.1 when we do this. So it will in other words, we can improve almost like 20% in terms of the axial resolution. Yeah. So with this, we also look at the mouse brain, and then in this particular example, we look at the thin skull model also. So we can actually identify the structure at the OCT images also. So these are some of the structure. This is the skull, and then this is the dura muscle. This is a very thin layer dura muscle, and then there are some structure like arachnoid space and subarachnoid space and gray matter and things like that. So if we look at if we scan a XY region, we can actually get the myelin fiber information because the myelin is actually highly absorptive, highly scattering. So they will appear like fibers if you look at the unfast view. And then similar as before, you can also extract the vasculature information from the OCT image. I'm going to talk more about how the information is being extracted in the OCT, the vasculature information. So if you're not sure like how you get the flow information just from the OCT image, I'm going to explain in a while. So this image is showing that just using OCT, you can actually visualize the vessels, and then you can also visualize the fiber, the myelin fiber in the cortex. But as you may also notice that if you use the visible light OCT for this kind of application, your penetration depth is going to be very shallow. So I'm talking probably like 400 to 500 micron. And then, but you can appreciate much higher resolution, as you can see that some of this structure may not be able to see in other wavelength or in other lower resolution variant. Yeah. So another quick summary of this OCT, visible light OCT. So we demonstrated that using visible light, we can actually push the resolution to be very high. And then with the asymmetric optical design, we can actually maximize the detection of the light without actually sacrificing the transverse resolution. Yeah. Lastly, I'm just going to jump into how we use the OCT, specifically visible OCT, to look at the retina of the human as well as rodents. Yeah. So here I highlighted that versus NRI OCT. So this is because most of the commercial and clinical system that you will find is mostly using near infrared light. So we're talking about maybe like in the 800 nanometer or 1000 nanometer wavelength. So they are more like the gold standard for clinical and commercial OCT device, because they are quite safe to send like NRI light into the eye. And today I'm going to talk about how we use the visible light and whether is it possible to send visible light into the human eye as well. Yeah, so a bit about eye. So the eye are the window to our soul. So this is a phrase that you might heard about it, and turns out that there might be some truth for it, because during the embryonic development, the retina and the optic nerve actually extend from the brain. So the eye is actually also part of the central nervous system. So it's like the phrase mean that like by looking at the eye, you can actually tell the emotion or the mind of the person. So maybe there's some link even in the biological perspective. Yeah. So the retina is actually composed of layers of specialized neurons that are interconnected. And then the light actually that go into the retina is captured by the photoreceptor, and then it actually convert to signal that actually sent through the optic nerve head to the brain for interpretation. Yeah. So this is how your eye looks like. Basically, it's a circular chamber with a lot of water inside, liquid, not necessarily, mostly water. And then there's a thin layer of tissue, which is the retina, is densely packed with the photoreceptor, and this is how your retina looks like using the OCT image. So if you see here, this is the region we call it macula lutea, macula. So this is where there's a very dense of the photoreceptor, and part which is void of the vessels, which is where your vision is the highest acuity. Yeah. So the motivation of using visible light as opposed to the NRI wavelength, which is the standard, is because as you still remember, the resolution is actually governed by the wavelength. So with this wavelength pushed down to visible light, you can actually get high resolution. And then it also gives you better contrast of the intrinsic chromophore. So this is a diagram showing that you can actually have a lot of absorptive contrast of the chromophore, like melanin or macular pigment, or even like photoreceptor rhodopsin and blood absorption, which you will not be able to appreciate if you use NI wavelength, because for NI wavelength, this chromophore are almost like transparent to an eye reflex because they are not absorptive in those regions. So the visible light also has been shown that you can actually look at the nerve fiber layer because in the retina there's a lot of nerve, and then there's been studies showing that the reflectance pattern of the nerve can actually predict some the health status of the retina in this case. So because when something goes bad in the cells, and the nerve fiber layer will break down, and then that will actually reflected in your reflectance spectrum. So of course, also mentioned a few times that oxygenation is things that are readily available if you use visible light, because you can extract the oxygenation information of the vessels. Yeah, and then one of the main motivation of the project is also we want to make this fiber-based. Yeah. So first, I want to highlight that this is a setup that we built. This is a free space setup. So later I will go into a fiber setup. But I just want to highlight two concepts here. So I keep saying that you can actually get the vessels or flow information, and then but how was it done actually? So basically, if you take a frame of the OCT image, which is the cross-sectional image, and then if you do a simple subtraction of two frames, which are separated by time. So basically, you take a frame of the same location multiple times, and you do the subtraction, and you will actually see there's some bright regime which actually correspond to the flow. So this because when the light actually hit on the blood and the vessels, right? They're actually highly scattering, and they are actually keep changing. So if you take out the static component, right, you're actually left with the vessels component. So this is how you can actually get the vasculature information, or in other words, you can get angiogram without actually applying a contrast agent into the vessels. So the flow is also another things that we can readily achieve, because when the light actually hit on the red blood cell and it get reflected, because the red blood cell is actually moving, so it actually the light reflected will actually have a Doppler shift. So it's something to do with like when you hear the sound of the train coming to you or leaving you, they are like different frequency. So this very similar concept. So basically it's a Doppler frequency. So you can actually measure it, and then you can actually infer the flow information of the vessel. So I hope I explain it in a easy to understand manner. So this slide is actually talking about how we can actually speed the saturation. So I'm not going to dig too deeply into this slide. Later I will show you one example how can you extract the so-called spectroscopy information of the tissue. Yeah. So of course when we try to do it in the mouse eye or rodent's eye, so this is quite a non-invasive approach, because you cannot draw the blood from the human eye and then like I guess one of the biggest questions people want to ask that how do you validate what you measure? So in this case, you can always fit something of your data and then you claim that you get this saturation value, but how can you tell for sure that your fitting is actually is true, is accurate in that case? So this one validation we did previously. So basically, but we can only do it in the red blood. So basically, we can actually manipulate the oxygenation saturation of the blood, and then we can maintain the pH value and the temperature, and then we can actually use our OCT technique to see whether we can actually predict the saturation value. And this is one validation we've done before that shown that we can closely predict from the OCT signal of the saturation value of the mouse blood. Yeah. Yeah. This graph is just showing that because of the equation that we use to fit, because the equation actually also depend on the concentration of the oxyhemoglobin and the hemoglobin. So we can also actually use the fitting result to actually determine the concentration of your hemoglobin in that sense. So meaning that we can actually obtain the hematocrit of the blood without actually using external machines or analytic solution. So this is just some retina imaging we obtain using the REX, and then and you can see that generally the blood vessels, they are very bright because they are highly scattering and absorptive. So but I just want to highlight to you that because the way of the blood is being the red blood cell is actually aligned to each other when they flow through at different speed here. So you can actually see that it also reflected in the OCT signal because of when the blood is flowing at high speed, right, it will actually create a shear stress or something like that. So the blood will actually align themselves, and it also reflected in the OCT signal. As you can see that there's this hourglass shape because when at the vessel wall, the blood is actually kind of like aligned to reflect the light better. But in the center of the vessel, the blood are not so aligned each other, so they're actually not so reflective in that sense. So this is why you see a drop in the OCT signal. So this is quite interesting that you may also observe in some of the study using OCT also. Yeah. So from this, we can actually fit the concentration of the blood in the retina, and then we can also get the oxygenation from the retina in the same approach in that case. Yeah. Yes. I need to go faster. So last portion of the talk just highlighted that we also did some work for human retina imaging using the visible light. So this is another schematic showing the system very similar to what you've seen. So basically we have a supercontinuous light source. We have some fiber coupler, we split the light, and then some of the light go to sample arm, some of the light go to reference arm. And then when they're reflected back, and then they're being sent to the spectrometer. So this is just a device I'm circling here showing the device we use to image the human retina. Yeah. So we characterize the performance. So back then when we actually started this project, we are actually the first that demonstrate the fiber optics visible light OCT because previously, most of the visible light system, they are free space because it's harder to make coupler which can actually work for broadband with us. So a lot of things are harder when you go to visible light as compared to NR wavelength. So the loss is higher, the operation bandwidth is shorter, the aberration is more severe. So everything is just get more difficult when you move to visible light from the near infrared light, because near infrared light is all optimized in terms of fiber technology earlier than the visible light. Yeah. Then I think a big question that people ask that is it safe to shine the visible light into the eye? So the eye actually could damage due to three mechanisms: photothermal, photomechanical, and photochemical. And based on the ANSI limit, we estimated that we can shine about 150 microwatt into the eye. So you can imagine like the first person that received this power, yeah, they have to take a bet like whether it will actually destroy the eye. So this is actually quite different from NI wavelength because usually you cannot see the NI wavelength, and they are quite transparent also. It's also a funny thing that in OCT research, right, you only use one eye for all your testing because you don't use both eyes because you don't know whether you will damage both eye one day. So at least you make sure that you only have one eye being used for the testing. So we done a lot of calculation, and also like to make sure that the power that we send is very low and then acceptable, that will not introduce any damage. But nowadays there are papers that describe that they send like 250 microwatt. So I would presume that 150 is very safe. Yeah. But the bigger question also, like how well we can measure this power, because the detector could be not calibrated well, or like because this power is actually very small. So to give you a reference, like what kind of power people send for the NI, right? So usually that could go up to 1 milliwatt or like 800 microwatt. So it's quite substantially different. So it is quite challenging to measure probably like low power in that case, and you have to make sure that when you measure it's 150, is it really 150 or is it like 180, something like that. So these are some considerations that you always have to be careful when you do like visible light. So we use the visible light to image human retina in vivo, and then we confirm that we can get less than 2 micron resolution. So this is actually not trivial for OCT, even though OCT is now very developed. And typically for the NI, even you want to get 3 micron resolution, the system have to be very optimized. Yeah. So and this is one such image we shown using visible OCT with 30 micro and watt when we use it for alignment. And then when we are happy with the alignment, we can switch to like high power, like 150 microwatt for the actual acquisition. Yeah. So this is one of the, I would say, one of the highest resolution of image that you probably can see in the literature that does not use adaptive optics. Yeah, correct. So adaptive optics is whole sort of topics that is not be worth another hour to talk about, but this is quite close to the highest resolution image you can see in the literature. So you can actually get quite a good contrast for all the different layers, and then all the layers in the outer retina as well. So just to let you help you understand, like all these layers actually correspond to different types of cells and in the retina, and then they all have different function and their thicknesses, and then their contrast are all could be important as a biomarker for a lot of the retina diseases. Yep. So some of you may actually heard about fundus imaging. So fundus imaging, so this black background and circular view is actually taken from fundus images. So basically what is this is you can actually use a camera to take a snapshot of your eye, but as you may expect, this kind of technology doesn't give you the kind of depth information. So what you get is actually a 2D information, but it actually still gives you a lot of information about your eye and your vasculature, in the sense that it can be a very very quick and non-invasive diagnosis way. But when we use OCT, right, we can actually capture the kind of depth information as you can see here, and then you can actually analyze the layer structure, which is not possible with the fundus imaging. Yeah. So I promised that I want to tell you a little bit like how we get the spectroscopy information. So this is just one example I illustrate here. So basically, when you capture such a broad bandwidth, right, you can actually split the bandwidth to half. Right? So for example, and then you can actually get like image of 2 color. in that sense. So by looking at the signal of the two different color, right, you can actually infer the information about the tissue. So this is quite similar to hyperspectral imaging, where you shine the object with different color and then you take the images. So but in this case, because for OCT, right, you actually capture all the color in one shot. So in this case, you do a digital post-processing to split the information to different color, and then you can actually get the spectroscopy information, like something like reverse engineering. So this is how you can get the spectroscopy information of the tissue. Yep. So in this case, right, I just want to highlight that what to see, for example. So in this case, because you split to different color, you can actually get different information. For example, in this layer, the retina pigment epithelium is actually a higher signal in the red color, because basically it's just that it is the longer wavelength can actually penetrate deeper into the structure better than the shorter wavelength. And but also it also due to the facts that the light is actually absorbed differently for different colors, so which also can give you information about the tissue. So based on the technique that I introduced to you, the Doppler, the oxygenation, and things like that, this is one of the, I think this is the first demonstration of using OCT, purely OCT, to get the oxygenation information from the vessels of human retina in a fiber-based technique. So you can actually get the flow information, and then you can get the oxygenation information of the retina. So why is this important? Is because retina is the most metabolic demand tissue in the body. So the amount of oxygen they use is the highest in the body. And then there's a lot of study that show that the metabolic state of the retina could actually be affected in some diseases, and there's a lot of effort trying to use this as a biomarker for like diseases, because people believe that when the metabolism is affected, it may actually show up quicker than the structural damage, which is more like when you are at the stage like it's non-reversible. So yes, I think very quick highlight what I present. So probably not going to talk too much on this slide, but basically already been summarized in some of the previous slide. So basically, to conclude my talk, so I hope by now I introduced to you some of the application of the neuroscience and ophthalmology for OCT. And then by using non-standard wavelength. So when I say non-standard, it means that non-near infrared wavelength. So we can actually realize some benefit. For example, we can actually show that we can actually improve the penetration depth, and we can also improve the spatial resolution if we go to like visible wavelength. But I think most importantly, we can now actually get like functional information from the tissue, because it used to be well known that OCT can only get like structural information, but with some of this added technique, we can now actually get like functional information like flow and oxygenation. So there's plan to actually combine this technique with multiphoton microscopy in our lab, as well as adaptive optics. So it will further enhance our imaging capability, especially when we want to look deeper into the mouse brain. Yeah. So thank you for your attention. I would be happy to take some questions if some of you may have some questions, but also happy to talk to you offline if you want to know more about how you can use OCT to further your research. Yeah. Yeah.
Thank you, Josiah, for your talk. And as Josiah said, we have now time for questions.
Josiah, thank you for a very nice presentation. I have like 2-3 very short questions. One question is, how long does it take to obtain an image?
Yes, correct. So usually OCT is very fast compared to like 2-photon or confocal, but then how fast is fast, right? So typically we're talking about like a few seconds to take a volumetric image. So that maybe but of course this depends on a lot of factors. For example, if whether I want to do like more pixels and things like that. Yeah, right. So it's quite similar to other technology. Like if you want to put more pixel, then sometimes you may have to take longer. But generally we're talking about a few seconds, like 2 or 3 seconds for a volumetric data of we're talking about in the millimeter range. So let's say I want to take 1 millimeter by 1 millimeter by 1 millimeter with a decent resolution, then usually we're talking about like a few seconds. Yeah. All right. So to give you some extent like how slow is other techniques, for example, for 2-photon it could be 1 frame per second, like, and then you take like 500. So it's like probably a minute. Yeah, correct, something like that. Yeah.
Okay, so it's very good at capturing like things in real time in a way, because I was thinking, you know, like if OCT could be used like to do something like a time lapse. So imagine, I don't know, like eye infection, retinal infection. Of course, you don't have the resolution to see like, you know, single cells, but definitely you will start seeing, I guess if there's inflammation, you will start seeing changes, right, in the structure. I'm thinking of the images that you showed so far. So if we had like inflammation, wouldn't we see some differences, for example, over time? Right? Or has it been used to study infection in tissue, for example, this method? And can you see like any difference like in the shadows or like, you know?
I believe I've seen some paper that use it to study the skin inflammation. So I'm not sure the kind of infection you're talking about is the same as what you are referring. So but I have seen quite a few papers that use it for dermatology, like they look at the inflammation and things like that. So yes, and yeah, I think the more important, always the first question that has to be addressed is like whether there's a contrast that you can get from the topic that you want to study. So it could be a structural changes, or it could be some kind of like so OCT is actually very good to measure. It's very powerful to measure structural changes. It's just that it doesn't allow you to do in a very specific manner. So you don't quite able to tell like what kind of cells like changes or things like that. Yeah, but you can probably tell the cells has changed, like bigger, smaller, the nature of some morphological changes. But yeah.
But it's better than using, let's say, 2-photon, because 2-photon kind of like is destructive for the tissue, right? In a way, I mean, you can apply 2-photon, but then it's kind of like more harmful. Whereas, like, as far as I understand, OCT is not harmful, right?
True. But I think 2-photon usually is quite, I would say, quite time-consuming. I would say. So, and then you have to go a little bit deeper, then it will get a bit challenging. So I think OCT is actually very good to do a site survey. And then like you can establish some kind of like target, and then I guess it's also quite good to monitor some changes. But depending on the type of contrast you need, then you can actually zoom in to get some kind of like 2-photon images, for example. Yeah, I think that's the complementary side of the OCT, I would say. Yeah.
Okay. All right. Thank you so much.
No problem.